Hi everyone. So today we're going to be going actually back to a topic that we covered at the beginning of the quarter, which is limits. So we're going to see that now that we know how to take derivatives, there's going to be a way to make taking certain types of limits easier. And it will actually also allow us to take types of limits that we were not able to take in the past. So I want to give you kind of a warm-up to think about. Just to kind of get your mind back on limits and remember how those work. So I'm going to give you two different problems and then we'll do each of them together. So the first one is going to be the limit as x approaches infinity of 2x plus 1 over x squared plus 5x plus 3. And then the second example is going to be the limit as x approaches 1 of x squared minus 5x plus 4, all divided by x minus 1. So take a few minutes, try to remember what the methods were that we used for each of these types of limits, because the methods for limits at infinity and limits not at infinity were actually pretty different. So take a moment, try to remember how that worked, and then come back and we'll go over them. So if you remember, the general approach that we used for limits at infinity was that if we go through and divide everything by the highest power of x that appears in the denominator, it basically allows us to take our limit and break it down into pieces where it's easier to calculate what the limit of each piece is. So we can go through and divide everything by x squared. And you might, know rules from pre-calculus or just kind of have figured out eventually that, if the degree in the denominator is bigger than the degree in the numerator, then the limit is going to equal, something. But as I mentioned when we were talking about this stuff, you're kind of at a point in math, when you're in calculus, you've kind of graduated to this level where it might be expected of you to know how to use certain methods in certain situations. So kind of the further you go in math, you start to do things that more kind of resemble proving things. And when it comes to proving things, there are certain methods that are acceptable and other methods that are not. And so in the case of this class, on the first test, when I tested about this stuff, I said, I will not give you points if you just kind of tell me, well, I know that if the degree is bigger than blah, 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 something like that. I wanted to actually see you use this method. So today we'll learn actually another method that I think is a little bit easier than this one that is similarly, a valid, mathematically sound method. So the next step here is to simplify each of these pieces. So we get 2 over x plus 1 over x squared divided by 1 plus 5 over x plus 3 over x squared. And then really the last step for this type of question is that you have to remember the fact that anytime you have a piece that looks kind of like this, so anything where the numerator is a number and the denominator is x to a power, the limit of that piece is always going to be 0. And so basically, because with limits you're allowed to kind of take the limit of each part individually, we can bring the limit inside and see what we get for each part. So here we get 0 plus 0 over 1 plus 0 plus 0, and then that is equal to 0 as our final answer. Okay, so let's try this other example. So this one, totally different. When you're taking a limit as x approaches a number, not infinity or negative infinity, it really doesn't make sense to do what you did over here. And that's kind of one of the biggest mistakes I see people make, is try to apply a method that doesn't make sense in a certain context. So here we want to actually see what we can factor and cancel out. There'd be nothing wrong with going and dividing everything by x, but it's basically not going to get us any closer to our answer. So in this case, we would want to see, well, the numerator can factor as x minus 4 times x minus 1. And so that allows us to cancel out this x minus 1. And so The reason that this works is basically that if you can simplify a function, you're not necessarily resulting with the same function, but its limit is still the same. So basically by canceling out this x minus 1, we got ourselves a new function that is defined at 1, where we can actually plug the number in. And even though it's not the same as our original function, its limit is the same because we've only changed the behavior at one specific point. So we get -3. Okay, so that's just our kind of quick recap of stuff from the beginning of the quarter. So now I just want to talk about some general kind of limit facts that you should know and that you can kind of use as facts, basically. So these are going to be kind of limits where you don't need to calculate anything or use any methods or do any algebra. These are just limits that, you know, if this type of limit comes up, you can just say, okay, well, I know that this is the answer for that limit. So limits that you should know. Okay, so first thing is if you are taking the limit of a continuous function, and specifically if your function is continuous at the number where you're taking the limit, well, then we know that you can just take the limit by plugging the number in. So that's kind of when you're working with limits, that's always kind of the first thing to try is, can I just literally plug the number in? However, that doesn't work with infinity. So I just want to make sure when I say x equals a, I mean like a number a. I don't mean infinity. It really doesn't make sense to plug in infinity because infinity is not a number. So that's kind of one fact we can know. So another one is that if you're taking the limit of a polynomial, and you're taking the limit as x approaches positive or negative infinity. So your answer is either going to be positive or negative infinity, and it's going to depend on the end behavior. So this is something I talked about back at the beginning of the quarter. There's a video about, basically the video about limits at infinity, I talk about this. So if you look at the degree and the leading coefficient of a polynomial, you can know kind of what that graph is shaped like and use that to tell you what the limit is. So like, for example, if you have an upside down parabola, well, that would tell you that both ends are pointing down towards negative infinity, right? So the limit in both directions would be negative infinity. So basically you just want to look at the shape of the graph and think about what that tells you about the end behavior. So end behavior is saying basically where are the ends pointing, and where the ends are pointing tells you the limits at positive and negative infinity. So yeah, a couple more. So actually for these ones, I want to draw a picture that maybe will help us. So the next few I want to look at, I'll write them down first and then we'll draw the picture. So I want to talk about the limit as x approaches infinity of e to the x. I want to talk about the limit as, and actually maybe I'll put this one here, the limit as x approaches negative infinity of e to the x, the limit as x approaches infinity of ln of x, and then the limit as x approaches 0 from the right, and we'll see why it's specifically from the right in a second, of ln of x. So for these four limits, to be able to kind of know them off the top of your head, I think the easiest way to know that is to be familiar with the shapes of the graphs of e to the x and ln of x. So if you took pre-calculus with me, you know I really tried to emphasize just being like having quick familiarity with the shapes of certain functions, and this is really one of the main reasons why. If you know what the graphs of certain functions look like, then you can just kind of visually figure out, oh, okay, that's what the limit has to be. So what does the graph of e to the x look like? Well, that one has a y-intercept of 1, right? And then it goes up. So from left to right, it kind of gets closer and closer to 0 on the left, and then it shoots up like this on the right. So this would be the graph of f of x is equal to e to the x. So it has a horizontal asymptote at 0 to the left, and then to the right, it goes upward. So what does this tell us? Well, that means that the limit as x approaches infinity of e to the x is infinity. And basically it's just because the bigger the number you plug in, if you take e and raise it to a higher and higher power, you're going to get bigger and bigger results. So e is like, 2.72. If you take 2.72 and raise that to the 100th power, you're going to get a really big number. And so that's why the graph points up, and that's why the limit is what it is. So what about the limit as x approaches negative infinity? Well, there the graph is getting closer and closer to the x-axis, so the limit is 0. And so that's because when you're plugging in, if you're doing like e to the negative 100, that's 1 over e to the 100. And e to the 100 is really big, so you have 1 over a big number, which is close to 0. Okay, what about ln of x? I think that one is maybe a little less intuitive for people, but the good news is if you have quick familiarity with the shape of e to the x, you can very easily draw the graph of ln of x using the graph of e to the x. So ln of x and e to the x are inverse functions of each other. And so what's the relationship between a function and its inverse when you look at their graphs? They're reflected over the line y is equal to x. So if you were to draw a diagonal line, y is equal to x, and then kind of take this green graph and flip it over that line, you would get a graph that looks like this. And this is the graph of ln of x. So if we look at the limit as x approaches infinity, so it's a little hard to tell from this graph, but basically it continues to go up and up and up. It just goes up really slowly. So the limit is still infinity because the graph isn't, it's not flattening out. It's not going down to 0. It's just kind of like slowly creeping upward. And then the limit as x approaches 0 from the right, well, why is it only from the right? It's basically because you can't take ln of a negative number, so there is no part of the graph to the left of 0. So if we look at what's happening to this graph, it's going down and down and down. So the limit as x approaches 0 from the right of ln of x is negative infinity. So those are some good ones to know. And again, like if any of these come up, you don't need to prove anything or do any calculations. These ones you can just say, okay, I know what the answer is. Okay, so next thing we're going to look at is taking the limit of fractions of different types of functions and kind of how those different scenarios might play out. And this is where we're going to get into examples kind of like the first two we did here, and then see a new way to take derivatives of things like that. Okay, so the next thing we're going to talk about is when taking the derivative, or sorry, not derivative, sorry, the limit, and maybe I'll write it like this, when taking the limit as x approaches a of f of x over g of x. And so in this case, I actually, when I write a here, this could be infinity or negative infinity. I'm just saying like any kind of limit. It could be the limit as x approaches 5. It could be the limit as x approaches 0. It could be the limit as x approaches infinity. It's just up here, and maybe I'll even write that here. So here we mean where a is a number. Okay. So basically, there's a few different situations that can happen. So let's say that the limit as x approaches a of the numerator is equal to a number. And let's say that the limit as x approaches a of the denominator is equal to either positive or negative infinity. So what's that going to give you as the overall limit? If the numerator limit is just a number and the denominator limit is plus or minus infinity, well, that's going to give us 0 as our overall limit, right? So an example of that would be something like the limit as x approaches negative infinity of 5 over x squared minus 1. Right, the limit of the numerator is 5 because it's just 5. And then the denominator, the limit of that would be infinity. And so if you have a denominator that's getting bigger way faster than the numerator, then your overall limit is 0. So if the numerator is just a number or even is 0, and then the denominator is going to infinity or negative infinity, then the overall limit of that fraction is 0. So maybe I should have written the word if here. Let me just, sorry, this will take a second. I feel like I could squeeze it in there. So if the limit as x approaches a of f of x is equal to c. Okay. So next case is going to be if the limit of the, let's see, what do I have next on my list here? Let's now say if the limit of the numerator is plus or minus infinity, and the limit of the denominator is a number, c. Then the overall limit is going to be either plus or minus infinity, and it's going to depend on the signs of what's involved, right? It depends on whether the denominator, it depends on whether the numerator is going to plus or minus infinity, and it also depends on whether the numerator is denominator is a positive or negative number in its limit. But regardless, either way, it's going to be going to either plus or minus infinity. So an example of that would be if you're taking the limit as x approaches pi over 2 of tangent of x over cosine of x. So the limit as x approaches pi over 2, and I think I should say here, let's say from the right. So the limit as x approaches pi over 2 from the right of tangent would actually, I think, be negative infinity. If you think about the graph of tangent, right, the vertical asymptotes happen at pi over 2. So, and I don't want to spend too much time on this, but go look at a graph and kind of convince yourself. So the numerator would be going to negative infinity, and the denominator cosine of pi over 2 is 1. And so this overall limit would be negative infinity. So just to give another example of, if the numerator is getting bigger and bigger and bigger and smaller and smaller and smaller, and the denominator is just a number, well, basically the numerator is going to be the main thing dictating where the limit goes. Okay, so those are kind of cases where you can know just by knowing that the numerator is doing one thing and the denominator is doing another thing, you are guaranteed to know your limit. Now, let's talk about situations where maybe you actually can't tell. So let's say you have a situation where the numerator has a limit of plus or minus infinity, and the denominator also has a limit of plus or minus infinity. So how can you tell what the answer is going to be for the limit? And so the answer to that is that there's no way to tell just right off the bat. For some functions, maybe there is, but like if this is the only information that's given, if all you know is that the numerator and denominator both go to plus or minus infinity, that doesn't tell you anything about the overall limit. So, we did an example like that earlier, right? We did this example here. If you were to take the limit of the numerator and the denominator both separately, you would get infinity in the top and infinity in the bottom. And so we had to kind of go through some extra work to figure out that the answer was 0. And if we had kind of played around with this, like if I change this to be 2x cubed, let's say, well, then the limit of the numerator and denominator, they're both still infinity, but now the overall limit would be something different. So it's really not enough to know that both the numerator and denominator go to plus or minus infinity. It really depends on the specific functions and kind of like, we'll get into this in a little bit, but which one goes to infinity kind of faster, basically. So if this happens, if you know that the numerator and the denominator both go to plus or minus infinity, then we say that the limit as x approaches a of f of x over g of x is called indeterminate. And that doesn't mean that you can't determine it. It just means that there's kind of more information is needed or other methods are needed. And we'll get into what those methods are in a little bit. And so same thing goes if, and so maybe let me just write down an example. So the example that we did earlier was, was the limit as x approaches infinity of 2x plus 1 over x squared plus 5x plus 3. And that came out to be 0. But again, this indeterminate doesn't mean that like there is no limit. It just means that you can't know the answer right off the bat, that you're going to have to do a little more work. Whereas some of these earlier ones, just by looking at it, you can know what the answer is without doing any algebra or any kind of calculation. So same thing goes if the numerator and denominator both go to 0. So if you get kind of 0 over 0. So if the limit as, let me give myself a little more space here. If the limit as x approaches a of the numerator is equal to 0 and the limit as x approaches a of the denominator is also equal to 0, then we also say that the limit as x approaches a of f of x over g of x is indeterminate. So an example of that would be the other one that we did. So the limit as x approaches 1 of x squared minus 5x plus 4 over x minus 1. If you try to plug in 1, you're going to get 0 over 0. And so we couldn't determine what this limit was without doing some extra work. But once we did that extra work, we figured out that it was -3. So the two that I wrote here already, this one and this one, these ones, we already have methods that we can use to figure out their limit. But I just want to write down a couple of other examples where we don't actually have those methods yet. So an example for the first one would be, so let's say that you were trying to take the limit as x approaches infinity of e to the x over x squared. Both of those limits are infinity, right? Like those both go towards infinity. And so we can't tell just from looking at it what the final answer is going to be. And so that is an example. And then there's no like algebra we can do, right? There's no way to simplify that. And so that's going to be an example where we're going to have to use this new rule called LHospitals Rule in order to answer it. And then another example for this type might be something like, actually, let's just leave it for now. We'll see more examples a little bit later. Okay, so next thing we're going to do is introduce this rule that's called LHospitals Rule. So LHospitals Rule, so it looks like it says hospital, but it's actually pronounced l'hôpital. So LHospitals Rule is basically a rule that allows you to take take limits of indeterminate forms. So if the limit, so let me actually say it this way. So if you are trying to find the limit as x approaches a of f of x over g of x, and the limit as x approaches a of f of x is equal to plus or minus infinity, and the limit as x approaches a of g of x is equal to plus or minus infinity. And let me just change this to the word where, because otherwise I'm going to have a gajillion ands. So if both the numerator and denominator are going to plus or minus infinity, and this, by the way, is sometimes referred to as indeterminate type infinity over infinity. It does not mean that the limit equals infinity over infinity. Infinity over infinity is not a number. It's just kind of a label that we can give to that type. Or if the limit of the numerator and the limit of the denominator are both equal to 0. And so this would be called indeterminate type. Zero over 0. So if you have one of these two situations, then you can apply L'Hopital's rule. And so what is L'Hopital's rule? It's actually really nice and convenient. It says that if you're trying to take the limit as x approaches a of f of x over g of x, instead of taking the limits of f of x and g of x, you can take the limit of, as x approaches a, of f prime of x over g prime of x. So this is L'Hopital's rule. However, it's really, really important to know that you can only use this rule if you have one of these two indeterminate types. So we'll see an example in this video of how this rule just doesn't work if you don't have one of these two types. So anytime, like I feel like students really like to latch onto this rule because it's easy and it's nice, but you can't just go apply it to everything willy-nilly. You have to always, when you're taking a limit, first pause and kind of assess what's going on with your limit and make sure that it fits one of these two formats. So it needs to either be like this or like this. If it's not one of those two types of limits, you can't use L'Hopital's rule. Straight up, you just can't. Okay, so let's see some examples of using L'Hopital's rule. And so the first one I want to do is actually one of the examples we already did. So we already, in the beginning of this video, we did the limit as x approaches infinity of 2x plus 1 over x squared plus 5x plus 3. And so we did it by doing that kind of like dividing everything by x squared trick. And now we're going to do it using L'Hopital's rule. So I want to just kind of give you some intuition behind like why L'Hopital's rule makes sense. So if you think about it, when you have a limit where both the numerator and denominator are going to infinity, basically you want to figure out which one is growing more quickly, right? If the denominator is growing more quickly, that's going to kind of bring down the whole limit and bring it down to 0. If the numerator is growing more quickly, then that's going to cause the limit to end up being infinity or negative infinity. So how do you measure how quickly something is growing? You use derivatives. And so you can think of L'Hopital's rule as a way to, instead of comparing your original two functions, if you're thinking of taking the limit as kind of a competition between the numerator and denominator, instead of comparing the original numerator and denominator, you can compare their rates of change. So that's kind of the intuition behind L'Hopital's rule. Okay, so what are we going to do? We're just going to take the derivative of the numerator and the denominator and take that as a limit. So what do we get? We get the limit as x approaches infinity of 2 over, and then the denominator we get 2x plus 5. And so now we're in that situation that we brought up earlier where if the numerator is just a number and the denominator is going to infinity, we can conclude right away that that limit is equal to 0. So I think this method's a lot faster, right, than the one we used earlier. But what's really nice about L'Hopital's rule is it allows us to take limits of things that we didn't know how to do before. So let's say we're trying to take the limit as x approaches infinity of e to the x, let's just say e to the x over x. So what might you guess for this? Well, if we're thinking about which one is growing faster, numerator or denominator, e to the x is a faster growing function than just x, right? If you plug in a number for x and then plug that same number into e to the x, you're going to get a bigger result for e to the x. So you might guess that this is going to go to infinity, right? Because the numerator is basically kind of lifting this whole thing up to a bigger number, and the denominator isn't doing anything to like drag it down. But how can we, officially tell that? We basically just take the derivative of the numerator, take the derivative of the denominator, and that tells us that we have the limit as x approaches infinity of e to the x over 1. which is the same thing as the limit as x approaches infinity of just e to the x. And that's one of the ones we talked about earlier in this video. So we can just know off the top of our head that, okay, that one is equal to infinity. So one thing I want to point out to you here is that when you're using L'Hopital's rule, you are not doing the quotient rule. So this is like totally different. Like basically you're not taking the derivative of this whole function, right? Or this whole function. You're taking the derivatives of the numerator and denominator separately. And so why is that? It's because, like I said, you're basically kind of, instead of comparing the original numerator and denominator, you're comparing their rates of change. And so you're really kind of thinking of the numerator and denominator as separate functions. So it's not true that like this function and this function are the same, right? Or that like this thing over here, this is not the derivative of the original function. But that's okay, because this is like a special rule for limits that says that specifically when you're taking a limit and only in these special circumstances, you can take the limit of the numerator and denominator separately. So I want to do a couple more examples. So let's do one now. Let's actually do that one, the other one from the beginning of the video. So this one I'd actually find kind of interesting. So the limit as x approaches 1 of x squared minus 5x plus 4 over x minus 1. So we did this one in the beginning of the video by factoring and canceling, right? But we can also do this using L'Hopital's rule because the numerator is going to 0, denominator is also going to 0. So that is situation 2, where you're allowed to use L'Hopital's rule. So that tells us that we can take the derivative of the numerator and the derivative of the denominator. So what does that give us? We get 2x minus 5 in the numerator and 1 in the denominator. And so we have the limit as x approaches 1 of 2x minus 5. And now we can just plug in 1. And so we get 2 times 1 minus 5, which is negative 3. So personally, I find this example really interesting because if we go back to the way that we did this example at the beginning of the video, we did it a completely different way, right? We factored and canceled, and so we ended up plugging 1 into x minus 4. And when we did it this time, we ended up plugging 1 into 2x minus 5. So we were taking the limits of completely different functions, but the answer still comes out the same. Okay, I want to do a couple more examples. So let's do this one. So the limit, as x approaches 1 of ln of x over x minus 1. So first thing we want to check is this indeterminate? So if we were to try to plug in 1, we would have ln of 1, which is 0, and x minus 1 would also give us 0. And so that tells us, okay, cool, we can use L'Hopital's rule here. So this tells us that we want to take the derivative of the top, derivative of the bottom, and that gives us the limit as x approaches 1 of 1 over x over 1. And so what is the limit as x approaches 1 of 1 over x? It's just equal to 1. So again, this is another example where we didn't have methods to take limits like this in the past. You know, in the past, if we had tried to do this one, we would have 0 over 0 and just be like, well, I don't know, it's undefined, we are stuck, we don't have any algebra we can do. And so now that we have derivatives, that's what allows us to come back and do it this way. So one more example I want to look at. And let me just find it in my notes. Sorry for the delay. So here we go. All right, so let's say we're trying to take the limit as x approaches pi of sine of x over 1 minus cosine of x. So as we said on the other ones, you always first want to check whether this is actually a L'Hopital's problem or not. So what would we get if we were to try to plug in 1? We would have sine of pi in the numerator, and we would have 1 minus cosine of pi in the denominator. So what is sine of pi? If we go on the unit circle and look at an angle of pi, so here's pi. The y-coordinate is 0, so sine of pi is 0. And then cosine of pi is -1. So we would have 1 minus -1. And so that actually gives us 0 over 2, which is just equal to 0. And so the answer to this limit is actually 0, because we can just plug the number in. If you plug the number in and you don't get something undefined, then great, then that gives you your answer. So the answer to this one is 0. So if we had instead tried to use L'Hopital's rule, let's say you didn't check, which you might not, right? Because you might forget. So let's say that you tried to do this using L'Hopital's rule. So you would say, okay, this is going to be equal to the limit as x approaches pi of the derivative of sine of x over the derivative of 1 minus cosine of x. And so that would give us the limit as x approaches pi of cosine of x over 1 minus negative sine of x. So that's 1 plus sine of, or sorry, the 1 goes away, my bad. Right, so you would have the derivative in the denominator would just be sine of x. And so now if you tried to plug in pi, you would get in the numerator -1 and in the denominator 0. And so this would actually end up being a limit that went to either plus or minus infinity. And actually you would need to kind of determine whether you're going from the left or the right to figure out if it went to plus or minus infinity. But I don't want to worry too much about that. My point is that this limit is not equal to 0. This would give us the wrong answer. This would give us either plus or minus infinity. So it straight up just doesn't work if you use L'Hopital's rule in situations where it's not allowed. So we'll get into some more examples of this in the next video. I think the rest of the videos this week will be a bit shorter than this one. So sorry if this one got a little bit long. But yeah, tomorrow's basically just going to be doing more practice with L'Hopital's rule. And then we really just have one more topic to